John and I have only just met, and being mathematicians, we need to get to know each other. So we're going to do that in the language that we know best. So let G be a group. And I'm going to define an invariant. So for every number n, I want to define an of G to be the number of subgroups h in G such that the index of h in G is equal to n. Now, G is finitely generated, then an of G is finite for all n, which means I can define a Dirichlet series for this. So I'm going to encode these as coefficients of Dirichlet series. So there's a kind of zeta function associated with the group. And what I'm interested in is how does the analytic behavior of this function reflect the structure of the group? Ping.
OK, so I'm interested in the geometry of knots and study topology. So suppose we have some knot, which is just some curve, gamma. In space. Now I want to define the distortion of this curve. So let's say we have any pair of points. I can take their chord. Then I can look at the distance along the curve between the 2 points and divide by the distance, the straight line Euclidean distance. And
that's just the metric on
yeah, so it's like the intrinsic, the big length divided by the straight line, the small length, at least 1. And I can take the sup over all x and y in the circle. So it's sort of like an inverse Lipschitz constant. And this is the distortion of that curve. Pong.
Excellent. I wonder whether I can turn mine over. Oh, I can. Great. If G is actually a nilpotent group, then something interesting happens because a nilpotent group can be written as a direct product of its Celoff P subgroups. So interestingly, the zeta function decomposes as what we call an Euler product over all the primes. So you can actually break this thing I'm interested in into lots of these local pieces. And so that's for any G, a nilpotent group over P prime. So this zeta G of P is defined as the sum. So it's basically a power series, a Taylor series, P to minus ns, n equals 0 to infinity. But the interesting thing for a nilpotent finitely generated group is that this is always a rational function. So this thing here is a rational function, which is the kind of unexpected discovery as a rational function. Pong, ping.
Great. So if I have like a knot class, so like not the specific curve, but just I want to consider all things isotopic to that curve. I can also define the distortion of the knot class as simply the smallest distortion over any curve which represents that knot class. So you can think of this as sort of a measure of the complexity of the knot. For example, the distortion of the unknot is pi over 2, and that's realized by the round circle. And the distortion of anything non-trivial, so if it's knotted, it's at least 5 pi over 3. And well, you might ask, how big can it be? Can it even, is there a universal constant? Like, can every knot be realized with, say, distortion less than 100? There are actually lots of knots which can be realized with small distortion. So for example, if I take sort of an infinite chain of these going around, it has the distortion of the infinite chain is basically the same as the distortion of one of them.
Right.
So, and you can make even more complicated examples.
But the question, oh, Pong, okay,
Yeah.
right, gosh. Yeah. So I guess my greatest discovery, I've been at mathematics a little bit longer than you have, but what I've kind of most proud of discovering in this whole context of zeta functions is, let me just see if this dries a bit. So I know you shouldn't write on a wet board. The Germans have a whole very sophisticated. Have you been given a talk in Germany?
No.
The sophisticated use of blackboards in Germany is amazing. They have all of this different equipment to do wetness and drying it and things like that. But anyway, we'll try this. Because if you define, so now I've let G be two different groups. I'm now going to define a very specific group. It's actually attached to an elliptic curve. So this elliptic curve is y squared equals x cubed minus x. And if you define a presentation, so this is a Hirsch length 9, dimension 9 group. So it's x1 generated by x1, x2, x3, y1, y2, y3, x, y, z. So it's defined by the following presentation. So this is the center of the group. If you do xi, yj, so that's a 3 by 3 matrix defining the commutators of this. If this is actually equal to, let's see if I get this right, x, z, z, and then we've got y here, 0, 0. So this group here.
So they're integers or something? Or
so these are generators for. Yeah, so these are generators for.
And this is the relation.
So this is a presentation. So
that's the relations.
That's the relations on my group. Excellent. Then what I discovered was that for each prime p, this group encodes the arithmetic of this elliptic curve. So it's actually equal to two rational functions, but plus the number of points on that elliptic curve. And as you know, that's one of the big open problems, is trying to understand these points on elliptic curves. So this is kind of a nice link between two completely different areas of mathematics, elliptic curves and nilpotent groups. So where this is the number of points. So it's the cardinality of xy in fp squared such that y squared equals x cubed minus x, which of course is the elliptic curve that Gauss did in his diary. It was the last entry of his diary. So ping.
Right. I guess I need some erasing.
You could probably turn yours over, but maybe you want to keep some of that.
I'd like to, I'd like to have some of it. So.
You're all following this one.
Yeah. Right, so I think distortion was first introduced or studied a little bit by Gromov. So this theorem is due to Gromov, and he proved that the round circle actually minimizes distortion among all curves, all closed curves. Like forget about the knot class, just curves. So he asked. Specifically, is the limit of the distortion of the PQ torus knot, which I'll define in a minute, equal to infinity. So as PQ go to infinity. So in particular, this is a specific class of knots with whose distortion goes to infinity. Each one of them is finite, but they go to infinity.
So that was his question.
Yep.
Yeah.
Mm-hmm. And so what's the torus knot? Also take some strands, and they don't let you be a topologist unless you can draw knots quickly. And then connect them up. So let's see. I've had 3 strands and 7 twists. So this is the 3-7 torus knot. And it's also the 7-3 torus knot. It's symmetric.
Okay.
So what I showed is that the distortion of the PQ torus knot is at least some constant, which is not particularly important, probably can be improved, times the minimum of P and Q. So in particular, this limit is infinity. So this
right.
solves this. Of course, it's also conjectured, one could ask, does, say, the 2p torus knot have distortion going to infinity? My theorem doesn't say anything about that. But one would think it does. So there's still more to be.
All right, but because the minimum is 2, you don't know whether.
Yeah,
exactly.
Yeah, there's still more to be seen. Pong.
Excellent. So I think we've got to know each other now, which is great. So if we could have 2 chairs, we'll have a conversation. So if somebody could bring 2 chairs up, that'd be great. What I was struck by when I was told about John's participation in this marathon was when I went online and looked at one of the talks he'd given, was the fact that he was doing it at a blackboard. It's what we've been doing for, I have a blackboard in my office. I love this as a texture for actually creating mathematics and actually explaining mathematics. And since this was meant to be a sort of marathon looking at practitioners, kind of ancient practitioners like myself and 89 plus practitioners, it was kind of curious to me that in mathematics, you know, that John's published a paper in the Annals of Mathematics, which is one of the top journals in our subject. It took me till I was 25 to publish in the Annals. You got there way before me. But actually, just the sort of things that, John, you're doing and the way you're doing it and the way you're publishing it is not that different from what I was doing and what I think, you know, people were doing maybe 100 years ago. So, I mean, your practice of doing mathematics, do you think as a post-89 mathematician, do you think it's any different?
Well, so I think like the internet's created a lot of efficiency in terms of like distribution of research. I can write a paper and post it online and everybody sees it immediately. Of course, this you know, adds a lot of noise, perhaps. And journals still serve their purpose of like recognizing work, but in terms of they don't serve the distribution purpose anymore. That is, you know, I can go online and find any paper I want, regardless of whether it's in a journal or not, very quickly.
Do you think that's kind of subverted actually the role of the journal, which was quite powerful before, because, you know, as you say, it's a kind of stamp of approval. You know, the fact if you get a paper in the Annals, people take notice. But actually, we stick things on the archive now, and that's where most people will see a paper for the first time. So is the journal just now a printed version of it, really just a mark of something to help you get a job? Or?
Well, so the stamp of approval that you mentioned is certainly still true. I mean, lots of papers on the archive are wrong, and
yeah.
But yeah.
Because we have this thing, the archive, which is where we basically put all our papers up as soon as they're published. And there's a kind of interesting politics about the archive because you kind of, although it's meant to be a very free space where people can upload papers as soon as they're done, actually there's a kind of, you do need to be part of an academic institution to have an email address to be able to register your paper there. So although it looks very free, there is a kind of, because they're very, you know, since I've put my head above the parapet and talked about maths to the media, the number of letters I get of people saying they've solved the equation to everything, you know, if those all go on the archive, then of course there's a lot of noise, and that's one of the problems. But
yeah, I think keeping out, I mean, so there is sort of a system where people with non-academic email addresses can post. I think probably I didn't have an academic email address when I posted the paper on the archive.
Really? Oh, that's so interesting.
Maybe,
well, you did it from a Gmail
not.
account?
Perhaps so.
Yeah, okay.
You can get, like, if you know someone.
Yeah,
you
I
can
think
say you're not.
Yeah, it's provided, but I think there is a kind of, there is a lot of noise out there, and managing that noise in this kind of internet age where you can get a voice very quickly, I think is a new phenomenon. That, Now, 89 is kind of interesting for me because that's when I finished my doctorate, and I was actually going on my first conferences. And one of my first conferences was in East Berlin, and actually, the conference was held in the ex-Stasi headquarters, and it had just been cleared of all and it was an incredibly kind of scary place actually to have a conference, because we were having it in rooms that had been interrogation rooms, and also politically it was a time, you know, there was a huge amount of Russian mathematics going on, which was actually quite hard to get hold of, because there was quite, you know, a lot of problems of distribution. And I went to a conference in 1991 in Barnaul, and then Irkutsk, in Siberia. But 1991 was when the coup happened. So when I arrived, the coup suddenly broke out, and all the Americans flew home, but I thought this was quite exciting, and so went down. But it was very interesting, because at that time, politically, because of the lack of information, there were a lot of discoveries that we realized Americans and Western mathematicians had made, but also Russians had at the same time. And at conferences during that period, there was quite I remember one conference descending into a fist fight, a literal fist fight between mathematicians over whose name was on that theorem, because the Russians said, but we proved it, but you didn't know about it. Now, I mean, so politically things were quite charged when I'd finished my doctorate, and for you, is politics an important part of the landscape of mathematics?
Well, so first, afterwards, could you tell me which theorem? I'm interested to know.
Oh, right, okay, yeah.
And it's really not something I think about at all in terms of the context of math.
Is that because of the ease of getting, if somebody in Russia now they can put something up online, they can get access to journals in a way that they couldn't before? Or?
Yeah, I think that's a lot of it.
Yeah. And what about technology? Because I suppose, we've both been affected by the role of the computer. There's a very interesting theorem called the four-color map problem, which is about if you take a map of the world, how many colors do you need to color all of the countries, so none of the countries that share a border have the same color. So what's the minimum you can get away with? And it was proved before both of us were on the scene, but using a computer, that 4 is the minimum. So you can't redraw the map of Europe and force 5 colors to be necessary. But this kind of caused quite a lot of tension in our subject, I think, about the role, a computer was used to do some of the proof. I mean, what's your view of, is that just me being an old fusty mathematician that says, well, you shouldn't use a computer, you should use this thing? Or what's your attitude to the role of computer proof?
I mean, in terms of like accepting the proof as true or something, I think right now computers are sufficiently developed that, we can
probably trust a computer more than trust this.
Perhaps so, yeah. I mean, there certainly are papers published in the Annals which rely on computer verification. For example. Also things with like hyperbolic conjectures about hyperbolic volumes. And the programs are publicly available, written for different architectures, and they all agree. So I think something big, which is sort of more long-term, like 50 or 60 years, it might be feasible, is machine learning getting to be at a stage where it can emulate a human and prove the theorem.
Be creative.
Yeah, and even write a proof that the human could read.
Right, yeah, which is... I think for me, one of the things about mathematics which I kind of love is a kind of universality of it. I mean, that, we both speak English, but actually we also both speak mathematics, so we didn't speak English. I mean, that conference I went to in Russia, I remember giving a paper to a room of people who didn't speak any English at all, but you can do this and they understand what you're doing. But also across time as well. I mean, there's a time element to this whole debate, post-89, pre-89, but actually, this probably would be understood in 1889, some of this. I mean, they would have appreciated, I think this, and yours as well. I mean, there's, and the mathematics that is proved here will be true when you do your marathon in 100 years' time here. There's a kind of universality about maths, which I think actually bonds us across country and across time as well. I mean, is that something that you...
Yeah, definitely. I think so, too.
What about, I mean, the one thing that does change, of course, is that new theorems come along. And when I started doing my doctorate, Fermat's last theorem hadn't been proved. Fermat's last theorem was this great unsolved problem. It was 350 years old. And it got, I remember the first sort of inklings that it might be about to be solved. And then Andrew Wiles, who's has the office next to me in Oxford, he cracked this thing. And But I think amongst the public, people heard this thing, Fermat's last theorem, they thought it was the last theorem, that we'd finished maths somehow. But of course, there are lots of unsolved problems, thankfully, for both of us. But it does seem to be a rather golden age, because Fermat's last theorem went, and we had the Poincaré conjecture by Grigori Perelman, another in your kind of subject of topology. But what are the big open challenges for you as a...
For me personally?
For you personally, well, yeah, rather than, the obvious ones like the Riemann hypothesis, but I mean, for you, things like trying to understand these knot structures.
Yeah, so, well, something else which was recently solved is geometrization, Thurston's geometry, which is, of course, follows from Perelman's work as well, and virtual Hawken conjecture. That's sort of more specialized to topology, but also another sort of big problem list getting virtually completed. But, especially with Fermat's last theorem, the techniques that were born out of these solutions actually have given rise to much more beautiful mathematics and more conjectures.
Yeah, I mean, it seems to be like one of these monsters. You cut off one head and two more appear behind. So it's an exponentially... the unknown seems to grow at an exponential rate. But,
my dad's thesis advisor liked to say it's mathematics is like an inverted pyramid. When you build up, you just have more places to build.
Right, yeah. And what about connections with other subjects? Because something that's very strong in the maths department in Oxford is kind of links with biology, and certainly physics has been tapping in. Do you think that's a new, the connections between subjects? I mean, science often stays in its silo, but I think individual silos, but I think now there's a feeling like there's more contact between departments. Is that what you're finding, or do you find still maths is where you want to be?
Well, so in terms of like maths and biology, I don't really know anything about that. I think I'm not really qualified to say. In terms of physics, I think, since Hilbert and before, we've been motivated a lot by physical problems. So like the can you hear the shape of a drum question, for example. If you know the sequence of pitches that arise when you strike a drum, could you know its shape? And there have also been, I mean, Ed Witten was the first physicist, the only physicist to win the Fields Medal, which is the...
Mathematics Nobel Prize,
Yeah.
And what about, you're actually a cellist as well, so maths and music go together, and obviously we're here in a place which is trying to bring together science and art. Do you think mathematics and art has got a sort of interesting future ahead of it? Or, I mean, the exhibition you have at the moment has got incredible mathematical themes running through it. I mean, it's,
yeah, well, I mean, certainly when, if I'm thinking about a theorem or trying to prove a theorem, there's a certain aesthetic aspect to it too. I can think of myself as an artist both writing down the proof and looking for it. So a great place for you to come and visit. So
thank you very much, John, for coming all the way from America to join us at the marathon. And I have one of my papers to give you as a present and inspiration, I hope. But that's one of it. Anyway, lovely to share the stage with you.